questions do you have? All right.
I had a question about that weird problem.
Sure.
You said it was like questions 10.
7, 9, and 14?
Yeah.
Yeah.
Is that 1.1?
1.1. Yeah. 1.1. Yeah. Yeah, 2 out of 1.1. Yeah, I guess the page, I probably don't have page numbers in the ebook, does it? Yeah, that isn't very helpful. Yeah, it's this end of section 1.1. Sorry about that. I guess I should go back and match up and make sure they really are the problems I want you to do, but they should be right. Other questions at all? All right, so last time we talked about some different properties of probabilities. Pardon me. Let's do a little bit more of the properties that we have. So remember, being a probability function, we needed to make sure that if we had any event at all, that probability had to be greater than or equal to 0. Pardon me. We said that the probability of the entire sample space was what? 1. Good. And if, I'll just do it for 2 mutually exclusive events. If you have mutually exclusive events, then what can you do with the probability of a union? Yeah, be adding them up, right? So it'd be the probability of A plus the probability of B. We can do that for any pairwise mutually exclusive events, but we can certainly think about it 2 at a time, right? So we have 2 mutually exclusive events. Then we can figure out their probability of the union by simply adding. We added a couple of, those are the 3 axioms, if you will, the 3 properties in the definition of being a probability function. But we also talked about a couple other theorems last time that helped us to write other probabilities. So for example, we talked about the probability of a complement. Remember, we use that prime notation for complement. How can you rewrite that? Yeah, 1 minus probability of A. Again, that's going to be helpful. We'll see that being helpful for us here in the next section when we start trying to count things up. A lot of times, not a lot of times, but sometimes it's helpful to be able to count how many ways something can't happen versus the number of ways something can happen. Those usually happen if you have, say, something like at least 1, because at least 1 means it could be 1, or it could be 2, or it could be 3, or it could be 4. That's a lot of things to have to try to count. The complement of being at least 1 is what? 0, right? And so it'd be a lot easier to count the number of ways that it can't happen than the number of ways that something can happen. So that this property will help us out later. We also talked about the probability of a union in general, whether or not they're mutually exclusive. How could you rewrite that? Good, minus the intersection, good. And again, if you think about it from a counting perspective, that makes sense, right? If I think about just counting the number of things in a union, I can count the number of things in the first set, I can count the number of things in the second set, but now I've counted the things that are in both sets at the same time twice, so I need to take off a copy of it. You can go through a formal proof of that, but I think it just makes more sense to think about it from a counting perspective, right? Count the number of ways that A happens, count the number of ways B happens. Well, now I've counted the number of ways that both happen at the same time twice. I need to subtract it off. All right, a couple of other properties that we didn't talk about, but we want to make sure does happen. That is, for any event, the probability of any event has to be less than or equal to 1. This actually is just a consequence of an earlier theorem, if you will. And I'll write this as a lemma. It's basically just to make sure that I can do a definition of what we may mean by a lemma. A lemma is a theorem itself. It's just kind of a helping theorem. Actually, it's probably better to say this is a corollary of this, but I just wanted to give it, make sure that we all have a definition of what this word means if I use it again. Okay. A lemma is a theorem. Usually, a lemma is used to help us prove a different theorem. Okay. So that's just what the word means. So, if I have two events and one's a subset of the other, then the probability really should be less. And now you can see why this theorem here is a consequence of this lemma. Certainly, any event is a subset of the sample space. If I use the probability of A that is less than or equal to the probability of the sample space, well, the probability of the sample space is 1. It's one of the properties that we have to have. So we can see why this follows directly from that. Okay. But let's see how we would prove this. We'll do proofs from time to time. So let's see how we would prove this. We talked a little bit about this idea before, but let me draw a picture of a Venn diagram again. But I want to make sure that I have the Venn diagram representing exactly this condition. If A is a subset of B, if I put the circle for B in my Venn diagram, if A is supposed to be a subset of B, where better I put my circle for A? Entirely inside, right? Agree with that? Okay. So now I can write B as two pieces. So since my A is a subset of B, we can write B as a union of two things. Notice it can be everything that's in A, but what's the rest of it? What have I left out? If I take A, what have I left out of B? What's this part here? What's this blank part that I didn't shade? You can say it in words, and then we go right into symbols. It's A complement there. Outside of A, so it's A complement and in B, right? So we can write that in symbols as B intersect A complement, right? We broke it up into two pieces, right? B, since A is inside of B, B can be written as everything in A, and then everything that's in B that wasn't in A. And we talked a little bit about that last time, right? Splitting a set into two pieces. Everything that's in the set that's also in another set, or everything that's in the set that's not in that other set. We talked a little bit about it last time. Now if we do the probability of both sides here, the probability of B can be expressed as the probability of this union. But we already talked about when we do probabilities of union, we can split it up as a sum. We might have to subtract something off, but generally speaking, we have a probability of a union as a sum of things, right? When don't we have to subtract something off? When don't we have to worry about the probability of the intersection? When the two events are what? Mutually exclusive, right? They have no overlap. Do these events here have any overlap? You said I wrote B as this part and that part. Do they have any overlap though? No, we got rid of the overlap, right? We took out the A part, right? These two things don't have any overlap. In particular, do A and A complement have any overlap? No. Okay. So since they don't have any overlap, I can write this as probability of A plus probability of B intersect A complement. I don't need to worry about subtracting off any intersections. And I'll write that in words off to the side because A and B intersect A complement are mutually exclusive. I don't need to worry about subtracting off the intersection at that point. Now remember, all we're trying to show is that the probability of B needs to be at least as big as the probability of A. Well, notice that we've got probability of B equals probability of A plus something. Can this something be negative? No, it's a probability, right? This has to be non-negative, right? It has to be greater than or equal to 0. So we're done. Probability of B here. I don't know why I don't have this expanded out, sorry. The probability of B here is greater than or equal to the probability of A because probability of B intersect A complement has to be non-negative. And we're done. That's the proof. I mean, again, if you think about what you want a probability function property to have, a property that you would want a probability function to have, I guess I should say, flip-flop my words around. Certainly, if one event is smaller than another, you would expect that smaller event to be less likely, or at least not more likely, right? For example, rolling a 1 certainly should be less likely than rolling a 1, 2, or 3. And this just makes sense. But notice that's not a definition property of a probability function, right? It's something that we can prove from the definition. And in mathematics, if you're able to prove something, you'd rather prove it than just assume it. The problem with when you start assuming too many things, besides what happens when you assume, the problem when you start assuming too many things is you might get contradictory statements, and you certainly don't want to be able to prove a contradiction. That causes a problem. Right? In particular, if you can prove a contradiction, then you can prove it in any one, and everything's true. Okay? Doesn't matter if you have a lie, you can imply whatever you want. Okay? So if you've got a contradiction, you can always imply whatever you want. So we don't like to assume too many things in math. We want to try to prove things that we can and only assume things if we have to. And at that point, when you assume something, we say that that thing that you assume needs to be independent of the other things that we've already assumed. And what that means is that if I throw in the statement or throw in the exact opposite of the statement, I don't cause any contradictions. That's what it means to be independent of something. That's the only time we'll assume something. Is that we literally cannot prove it and cannot prove its contradiction and can actually show that we can't prove those things. Okay? That they're independent of each other. That's a discussion for a different day, but I just wanted to mention why. Certainly it makes sense intuitively that as the sets get bigger, they should be more likely to happen, right? That's intuitive, but we never proved it from what we had for the definition. All right, sorry I went off on a tangent, but I'm allowed to do that. I'm in math class, all right? I know some of you have already heard that joke before. Some people haven't had me in class before. You got to hear a new joke. That's new to you for the joke, right? Anyway, sorry. We wanted to make sure also that we did it prove. Okay. One last little property that we can talk about is just an extension of the union idea as a theorem. This talks about the probability of a union of 3 things. Well, you can probably guess if they, well, it's not a guess. If they were mutually exclusive, then I could just add the probabilities together, right? If they are pairwise mutually exclusive, then I can just break it up as a sum. But we know that generally speaking for a union, I can't just do the sum. I end up double counting things, right? So notice that there would be some double counting for A and B. There would be some double counting for B and C. And there would be some double counting for A and C. However, at this point, we might have subtracted some stuff off too much. In fact, we have. Okay? What we've ended up subtracting off too much is the set of stuff that is in all three of them at the same time. So we end up having to add it back. So at the end, you would need to add back in the probability of A intersect B intersect C. If you wanted to actually, I'm not going to go through the proof. If you actually wanted to prove this, okay, the way you would start is just use your breaking of the probability of the union of two things. Just group two of them together, and then start by that. And then just keep going. Okay. I'm not going to do it. You just play around with the algebra. Okay. That's how you would start. Okay. Does that make sense? Okay. Another way to think about it is if you think about the Venn diagram and how the different things add up or line up, overlap, you can start thinking about, well, I count this, this, and this. How many times have you counted each region? And then try to subtract them back off, and you'll realize you subtracted that intersection region off one too many times, so you have to add it back. It's another way to think about it. I'm not going to go through it because I don't want to take the time. All right. So going back to the problems that we worked on before, you could either do it with that particular property. Oops, this is the one I wanted. Or do it with a Venn diagram, either or. So let's look at this particular one. Where we've got a whole bunch of different, looks like a whole bunch of different categories, but really we only have 3 categories that are going on. So this one says that you've got 10,000 policyholders at an auto insurance company. The reason why they've got these classifications to start with is basically so that you're talking about sets of their complements. So the first one talks about that you can classify a policyholder as either young or old. There's no difference, right? So what we mean by that is that I don't need a set of young and a set of old, because the complement of the young would be the old. Okay? Male or female, again, don't need to classify male and female separately, because if you're not male, then you're female. Just from this scenario. Same idea with married and the same. Okay. So, again, so we can think about this as looking at unions of things and breaking things up into pieces. Notice that this part right here is talking about the number of things that would be in an intersection, right? Agree with that? It says 1,300 young males, so that would be your, pardon me, intersection of young and male. This would be an intersection here as well. This would be an intersection with this here as well. Finally, we've got young married males. That's an intersection of 3 things, isn't it? Okay. So this is asking us for young, female, and single. So in the young set, not in the female set, or excuse me, not in the male set, and not in the married set, if we go by young, married, and male from what they gave us. All right, so you could use the formula that we just came up with and go through that stuff if you really wanted to. I think it's a little bit easier to see it with a picture, personally. Okay, so what I would do is make a Venn diagram. Because all of the numbers Let's do male up here, just because the male was first. Doesn't really matter. Because all of the numbers they gave us were in terms of young, male, or married, and or married, I should say. I want to make those my 3 sets. Pardon me. Now, first off, my rectangle here is denoting my entire space, if you will. I want to fill every single region in here with a number. How many regions do you see? How many different non-overlapping regions, I should say? How many different regions do you see that don't overlap at all? 8 total? 1, 2, 3, 4, 5, 6, 7, 8. Okay? When we have these counting, or in the next one we'll do probability problems that I can do with a Venn diagram, I want to try to fill in each of these little spots with something. Okay? That's the idea. Now, added all together, if I take every single number and add them all together here, what should it total up to when I'm done? It should be 10,000. It should be all your policyholders, right? We agree? So let's start figuring out how we can fill this in. Well, notice that this is the entire young circle here. If I look at that entire circle here, what should that add up to? 3,000, right? Because it tells us there's 3,000 young. We agree? But do I know how to split that up into those 4 regions yet? No. Likewise, do I know how to split up the 4,600 that should go in this circle? Nope. Do I know how much? And I don't know the same thing for the 7,000, right? We agree? I don't know how to split that up yet. Likewise, if I look at the part that I put the little box around, the young males, what region or regions would represent young males? It might be more than one region. What region or regions represent young males? Yeah, it's the overlap between young and male, right? It's this little sliver here. But again, how many regions is that made up of? 2. So do I know how to split up that 1320 yet? No. Likewise, here's married males. I don't know how to split that number up yet. Likewise, that's young and married, right? However, the final thing that they gave us, 600 young married males. Can I put that number directly into a region? Yes, because that's the line that's right directly in the center, right? This is pretty indicative of how these types of problems go, by the way. Usually, not always, but usually they will give you a number that you can fill in the middle, and then you work your way around, work your way inside out, okay? Let's go back to the piece that I boxed. You told me that that's this sliver, but now we've counted how many of them? 600. So you know how to fill out the rest of it? What would you do? Yeah, it'd be 720. We're doing that subtracting. It's a complement, right? This whole thing is 1320. We've counted 600 of it. The complement of that is it has to be the rest of it. It has to be the 720, right? It's a counting versus a probability, but they go hand in hand, right? It's the same idea of doing the probability of a complement. This would be 720 here. We have married males. We would subtract again. So that's what? 2410? Right? Because it has to add up to the 3010. So subtract. This would be 800 here, because total together they have to be 1400. We agree? Yep. Okay. And now can we figure out what's in each of these little regions now, here, here, and here? Yeah. What are we going to do to figure out, say, this region here that's the rest of the young circle? What would you Yeah, good. I'll take the 3,000. It was 3,000, right? I don't see it on the screen because it's off the top. 3,000 total and subtract off those three, right? 14, what, 2120? Subtracted to give you 28, 880? Did I do that right? I try to do the arithmetic quickly in my head and mess it up, guaranteed, at some point. Okay? 4,600 are male, do it the same way, but pardon me. This is 3,010 plus another 720 is what, 3,730. Subtract that off, you get what, 870? Did I do that right? Yeah. Yep. I like when I get nods that I did it right. It makes me feel a little bit better. All right. What'd you get for the last one? I see Justin has a calculator. 3190? Yep. Okay, cool. We have 7 of the regions figured out now, right? Can you figure out the 8th? How would you figure out the 8th? Yeah, 10,000 minus all of those, right? Did we figure it out yet? We're all looking at Justin. Yeah. How did you figure out which one? The males. 720 plus 600 plus 2410. And then subtracted it from the 4,600. Yep. 530, is that what you said? Okay. I'll trust you. By the way, you could have got to this number here by using our formula that we had, right? Because I know that the number of things that have to be in the union of all three would be 3,000 plus 4,600 plus 7,000 minus 1,320 minus 3,010 minus 1,400 and then plus 600 back again. That's using that property we talked about a little bit ago. But I think the picture helps because you can do it very, very systematically. Personally, I think it's better. Okay. All right, now it's just a matter of what are we asked? What's the problem asking us for? Young, female, and single. What region are you looking at? Say it again. The 880, yeah. It needs to be in the young circle, not in the male circle, not in the married circle, right? Young, female, and single has to be in the young circle, not the male circle, not the married circle. So it has to be the 880 here. So that would be your answer that you're looking for. Okay. Okay. Let's look at the next one because it's similar. This one's given as probabilities versus counting things. But it's the same premise. You've got vision, you've got dental, and you've got long-term care. So I'll just make it circles for those, just like we did. Let's look at the very, very first, before we start putting numbers in, let's look at the very, very first thing they tell you after they tell you that you have 3 types of insurance. Employees who enroll for insurance must enroll for at least 2 coverages. We should now be able to fill out certain regions pretty quickly. At least 2 coverages means you have to be in where? If it says if you enroll, you have to enroll in at least 2. So if you have insurance, what regions on your picture would you have to end up in? Be in one of the overlaps, right? You have to be in one of these things, right? Agreed? So can you be in here? Nope. Can you be in here? Here. What would you fill out those with numbers then if I can't be here, here, or here? Zeros. Yeah, those probabilities have to be 0. Good. Don't have anything in those regions at all. Because it says if they enroll in insurance, they have to be in at least 2. Could be 3, but it has to be at least 2. Okay? All right, let's see how we figure out the rest of it. Can I use the first property that they tell you directly to put in a number? No, because why? Why can't I use the first number? Why can't I just plop in the 0.4? There's 3 regions, right? These all together have to add up to 40%, right? But I can't just plop in the 0.4 or 40%, whichever way you want to write it. I'll write it as a decimal because our probability should be between 0 and 1, so I'll write it as decimals. Okay. Likewise, we can't plop in the 80. We can't plop in the 70. What can we plop in? The 20, right? The 0.2, right directly in the center. It says the probability of doing all 3 is 0.2. Yeah? Now we should be able to go out, spiral out from that, right? This represents the rest, this part right here represents the rest of vision and dental, right? So what's going to go there? Or do we know what goes in there? I still have a problem, don't I? Because I still have to have this plus this has to be 40, doesn't it? Okay. All right. So how might we attack this then? I know that the 0.2 definitely had to go in the middle, right? Without a doubt. But how might we attack it? Well, there's still 4 pieces that we have to figure out, right? So sometimes it might be helpful just to start setting up some equations that you know and see what has to happen. So let me just use some letters to denote the different regions. Maybe. Let's say I'll do X, Y, and Z for those pieces. Give me some equations that you might have involving the X, the Y, and the Z. Good. X plus Y plus 0.2 has to be 0.4, right? We know that the total of the vision insurance is 0.4 or 40%, right? So when I add all of those things together, I have to get 0.4. What's another equation? You're thinking about the right thing. Is I don't know that those would add up to 1. We'll get to that here in a second. You're exactly right, though. You're thinking about a good thing. We're just not quite there yet. You're right. Can you do one with the X and the Z by itself? Good. X plus Z plus 0.2 equals 0.8. Can you do one with just the Y and the Z? Yeah, the Y plus Z plus the 0.2 has to be 0.7. Now, I do want to think about the one that equals 1. X plus Y plus Z plus 0.2. I got one more region, though, to get the equals 1. It's that part out there, right? But that's the part that we're actually looking for, isn't it? So if I called it, say, W, then I would know that x plus y plus z plus w plus the 0.2 equals 1. That's always a good one to think about. It's a good one. You're exactly right. You just had that extra region that was in there. Okay. Notice here, I now have enough information to solve this, by the way. Right? Pardon me. Because I want the W, right? But I have 4 equations and 4 unknowns. I now have enough information to be able to solve this. Theoretically, I should have enough information to be able to solve it, right? Do I need to know, and this is actually it's kind of smart to think about, what, especially if you're thinking actuarial science, you may not be thinking actuarial science at all, but in general, if you're in some area where you may need to take a certification exam, teacher, engineer, actuary, any kind of that thing that has a, any kind of certification exam, problem solving ideas are smart, right? Don't do more than you have to do if you're on a time limit for a test. This problem is asking you for W, right? You could not care any less about what x, y, and z are. As a matter of fact, if you can figure out what x plus y plus z is, you're done. Right? Okay? Look at these equations. Each equation, well, 2 of the equations have an x, 2 have a y, 2 have a z. If I add those 3 equations together, I'll get 2 times x plus y plus z. So I don't have to solve for x individually, y individually, z individually. I need to solve for their sum of things, right? So if I add those 3, I can get rid of it. By the way, you can subtract your 0.2s over. But if you add these 3 together, you'll get 2 times x plus y plus z equals what? What I have 0.2 plus 0.6 plus 0.5. 0.2 and 0.6 is 0.8 plus a 0.5 is 1.3. All right, when I add those, I subtracted the 0.2 over. 0.2 and 0.6 is 0.8 plus a 0.5 is 1.3. Divide by your 2 now. X plus y plus z has to be 0.65. Now you can plug that in for this whole thing, because all I care about is W, right? Plug that in and subtract, you should get W as 0.15 when you're done. So the probability of not enrolling in any insurance is 15% or 0.15. That saved me a lot of time for having to figure out what X is, what Y is, and what Z is before I figure out what W is. When all I cared about was what W is. That makes sense? This might have been one, by the way, where the picture I think helps. Personally, I like the picture because it helps me organize my thoughts. But this might have been one where it might have been just as easy to do the formula. Because notice that if I did the probability of V union D union L, what's all in those 3 sets? Well, maybe not, because I don't have the intersections. I thought maybe it would be easier. If you were to use the formula, it may not be any easier. That would be what the formula looks like. Right? I still don't know what these are. I know what these values are. I know what this value is, but I still don't know what those are. So he still would have had to do some work to get to that. But now notice that you want the complement of this. You would do 1 minus that to get when you're done. Anyway, you could also use the formula. This is what the formula would look like. Personally, I just think the picture helpful with organize thoughts. Questions on that? Is okay? If you've had discrete, you've probably done problems like this. And if you haven't had discrete, you may have still done problems like this. All right. Let's go on to the next section then. The next section talks about methods of enumeration. You also get it warm. Get hurt off a little bit. I get excited about teaching math though, so I should get warm. I better get excited about it. I've been doing this for, what is this? Holy crap, year 27? And that's just after 5 years of grad school and 4 years of undergraduate. So, I've been doing it a while. But it's fun. I like it. All right. Anyway, we've talked about a lot of the things that we have to do to be able to do probability, especially from a discrete standpoint, is to count the number of ways that you can have an outcome, count the number of things in your sample space, and then also be able to count the number of ways the event can happen that we're interested in. So being able to count is very important for being able to figure out discrete probabilities. Now, when we do continuous probabilities, it's going to be very important to be able to integrate. And Izzy gets cold immediately, sorry. If we need to turn it back on, we will. No, it's fine. This building is, what, 123-ish years old? Something like that. And, of course, it got retrofitted with heating. So, it's sucky. Not to put too fine of a point on it. One interesting story is that all of these windows, when they replaced them back in the 80s, they're literally, every single one of them is a different size. They all had to be custom made and put into each individual spot because back when the building was built, the way you put in the windows is the bricklayers would go and just leave a hole. They wouldn't be exact about how big the hole was. So then you had to put the windows in individually. So all those windows are all different sizes, just as an aside. So, all right. Anyway, again, going back to what I was mentioning, talking about, to be able to do discrete probabilities, being able to count is important. All right. So that's what we're going to talk about in this section is just how do we count things. Okay. One of our big principles that we'll use is what's referred to as the multiplication principle. Basically, there's two big principles we'll use. Even though we'll talk about some special instances of the multiplication principle that make it sound like we're doing a couple of different things, or several different things, really there's two big principles for counting. One is when do you multiply, the other is when do you add. Okay? So there's a multiplication principle, there's an addition principle. All right? The crux of the multiplication principle is pretty straightforward. If task 1 can be performed in m ways, and task 2 can be performed in n ways, then the number of ways to perform task 1 followed by task 2 is m times n. That's all the multiplication principle says. Or that's all the multiplication principle says. Task 1 you can do 5 ways. Task 2 you can do 4 ways. Well, that's great. I've just noticed that there's a broken chair back there, and I teach a class of 30 students in here, and I need every single chair. I need to make sure that I get a different chair for tomorrow. Sorry, I just happened to say that chair is definitely seen better days. Holy cow. That's destroying. Great. Okay. Sorry. I also get easily distracted. All right, so if you do task 1 in 5 ways and task 2 in 4 ways, task 1 followed by task 2 is 20 ways, 5 times 4. All right, so that's all the multiplication principle says. So, for example, if you roll two dice, two 6-sided dice, how many possible outcomes do you have? 36, right? Because there's 6 ways to roll the first one and 6 ways to roll the second one. Multiply, you get 36 possibilities, right? So from there, you might need to be able to count things like rolling a 7. What's the probability of rolling a 7? Now notice that's a little bit different, right? Because how can you get a 7? You can do 1 and 6, 2 and 5, 3 and 4, 4 and 3, 5 and 2, 6 and 1, right? There's 6 ways to do that. Right. So notice that's a little bit different. That's not a multiplication thing, right? Because you got an or in there. And that's where the addition principle is going to come up from. Is if you have an or, you'll break it up into mutually exclusive kind of things and add them. So anyway, that's the multiplication principle. Like I said, it's pretty straightforward. So we're going to have things where we'll need to use the multiplication principle kind of sequentially, and then, pardon me, and then being able to use for particular formulas to do the counting for us. But before we get to that point, let's see if we can look at, this is an example here in the book. It says how many four-letter code words are possible using the letters from the word Iowa. I'm really surprised here that they would use Iowa as one of their examples in the textbook, considering, like I said, one of the professors was or one of the authors was a professor in Iowa for many years. Okay. All right. Well, notice there's two different possibilities here of being able to select these letters. Maybe you select the letters and all you're looking for is a rearrangement of them. Or maybe you're allowed to repeat the letters. Maybe you could use I, or OW, right? So there's two possibilities, so that's actually what they want to do in the problem is, first part says, if repeated letters are allowed, or no repeats are allowed. All right. All right, so notice that the repeated letters are allowed are like rolling two dice, because I could think of rolling two dice as the same thing as rolling one die and then picking it up and rolling it again and making sure I record what the first outcome is and what the second outcome is. Right? Those would do the same thing. Right? So that's kind of repeats are allowed kind of idea, right? Because if you roll a die and then roll it again, you might get the same number twice. That would give you repeats are allowed. So this first case is just exactly like what we just had for the dice rolling. We have 4 tasks in this case instead of just 2. But the multiplication principle would still apply. You would do task 1, then task 2, then task 3, then task 4, and multiply them all together. So what would you have in this case? How would you figure out part A? Good, 4 times 4 times 4 times 4, right? So for part A, you would just have 4 times 4 times 4 times 4. You get 256. Generally speaking, if you have repeats are allowed, you kind of have to do the multiplication principle. There's not any typically fancy formulas to use along those lines. Versus, if we have repeats are not allowed, no repeats are allowed, I can still think about it as tasks, but notice that my possibilities for the next task go down, all right? So if I think about it as tasks, how many ways do you have to do the first task? Or how many ways do you have to pick the first letter? 4, right? But once I pick that letter, I can't pick it again. So how many ways do you have to do the second task? 3, good. And then the next one, 2, and then 1, right? You get 24. Significantly fewer. Okay. All right. So that's the difference between repeats are allowed, repeats are not allowed. For those of you, I'm guessing most of you, not all of you, probably recognize the 4 times 3 times 2 times 1, the factorial idea, right? Okay. So this would be 4 factorial here. And if you've had discrete or have had some counting ideas, that's a permutation idea, right? No repeats. Order is important. If it's a code word, or think about typing a pin into an ATM, right? The order would be important. You're going to type your pin in the ATM. You don't want to put the digits in the wrong order, right? Same idea. So that's no repeats. Order is important. That's a permutation, and then we can have a special formula for that. So as a definition, a permutation of n objects taken r at a time is an arrangement of these R objects where repeats are not allowed and the order of selection, order of the arrangement, order of the selection is important. That's the big thing about a permutation. Permutations, repeats cannot be allowed. If repeats are allowed, you most likely need to use your multiplication principle. There are some other formulas you can do if you've got some indistinguishable object ideas, but that's I'm not sure how many problems there are actually in this book. It's more of a discrete topic. Repeats are not allowed. Is a permutation, could be a permutation if the order matters, right? So again, if you're thinking about making codes, the order would matter for the code, right? If you have your password, for example, you got a new computer, you can't just rearrange the letters and still have the same password. Unless you're using a password that's like A, I mean, it doesn't matter what order you type it in. Anyway. All right, so how can we figure out a formula for doing this? Well, we just said here that in this case, we used all 4 letters, right? And we had 4 times 3 times 2 times 1 that gives that 4 factorial idea. What if we said we wanted to make a 4-letter code word from maybe A, B, C, D, E, F, G, H, I with no repeats. And again, since it's a code word, the order matters. Again, here we have tasks to do. I got to pick the first letter, then pick the second letter, then pick the third letter, then pick the fourth letter, right? How many ways do you have to pick the first letter? 9, yeah. And then once we pick the first letter, can't use it again, so how many for the second one? 8, and then 7, and then 6, right? Agreed. Now notice this starts like a factorial, but it doesn't go all the way down because we stopped at 4. Right? So, but we can still use the factorial piece idea, if you will. If I had the factorial, let me put this in red. If I had, whoa, hey, that's huge. Don't need that big. If I had the factorial, we would still have we'd have a 5 times 4 times 3 times 2 times 1 in there, right? We would not want that, correct? So I could also put that in the denominator, and then they would cancel, right? So notice now that on top of this fraction, I have 9 factorial. We're dividing out by 5 factorial. Where did that 5 factorial come from? Well, notice we took 9 objects. We rearranged only 4 of them, but these 5 factorial would be the other ones kind of rearranging, right? And we don't care about those. So I can think about this denominator as being kind of a complement idea, if you will. And I can think about it as 9 minus 4. So notice that this value here is the number of objects that you have, the n. This part here is the number you're selecting. So this gives us a formula. Let me see what's, okay. So this formula that we have, the notation is NPR, like this. You may also see P of NR. The formula for doing this would be n factorial over n minus r factorial. And this is what I said. This is really just a multiplication principle. You don't actually ever have to memorize the formula. Now, the next one we have, I would either memorize the formula or figure out where the button is on your calculator. Okay? But you could do this with just multiplication principle like we started, right? So all this is doing is I'm starting off my factorial and I'm just canceling out a piece that I don't want. It's just the multiplication principle in a shorthand notation. We are okay with factorial, yes? Okay. Just making sure. All right, cool. All right, so far so good? All right. So what happens if repeats aren't allowed? Okay. Well, for example, let me do a shorter example. Goodness, sorry. Let's say you wanted to make a 2-letter code from that Iowa idea again. No repeats. Okay. We should actually be able to list this pretty quickly, but we're going to. How many ways would you have to do it? Well, again, we've got, if I want to do a code word, then an order would matter. You'd have 4 ways to select the first one, 3 ways to select the second one. You'd have 12 total, right? And again, we should be able to write this out pretty quickly. Oops. Let me actually write out the one I wanted. Okay. Those would be the 12 possibilities, wouldn't they? Just took the first letter, matched it with each of the remaining 3, took the second letter, did the same thing, so on down the line. There's 12 possibilities. But what if I decided that the order didn't matter? Maybe instead of making 2-letter code words from 4 letters, maybe I said, I've got 4 students and I need 2 of them to help me move a table. Does it matter in which order I pick the 2 students to help me move the table? No. I just need to pick 2 students, right? So it doesn't matter if I pick Austin and Izzy first or second, or vice versa. Those will be the 2 I selected. Yeah? Okay. All right. So if the order doesn't matter, then I've got things that match up. Let's circle these in red. These 2 match, right? These 2 match. Getting crazy here with my circles. Those 2 match. Oh, those 2 match. Those 2 and those 2. That was super informative. But the important part here was they all occurred in groups of 2, right? In particular, once I pick one arrangement, if I rearrange those letters in any order that I want, I get the same selection, right? Do you agree? I get the exact same selection no matter what it is. Yeah? Okay? So notice that the number of ways to rearrange these things would just be 2 or 2 factorial, right? If I've got those 2 objects and I just want to rearrange them, it'd be 2 factorial. If there were 3 objects, the way to rearrange those 3 objects would be 3 factorial, and so on down the line. So the way that we can do with, or when the order doesn't matter, we can just divide out by the number of rearrangements of the thing after we've already selected it. Okay? So let me give a definition and then a formula. A combination of n objects taken r at a time is, pardon me, a selection of r objects with no repeats, and the order of selection does not matter. Okay. So the formula for this, the notation is NCR or C of NR. That's another notation. Or, and this will be this notation that I will use, and you may have seen this in other contexts. You put the N and the R vertically, and then parentheses around the whole thing. The way I say this typically is N choose R. Well, I'll typically say it. These are also called the binomial coefficients. The reason why they're called binomial coefficients is because these numbers naturally come up in the expansion of binomials. Okay. The formula is we do n factorial and n minus r factorial because that would be the permutations, right? That's the number of ways to do this in order. We just talked about that, right? But once we do that selection, the order doesn't matter. So we would divide out by the number of arrangements of those R objects. Yes?
So how do we need to apply a combination? Is it the last statement or it doesn't matter?
It'll always say you'll apply combinations if it's no repeats and order doesn't matter. So it should be in terms of the context of the problem. Okay. So good question. Let's go ahead and start asking those questions as we do some problems here. All right, so let's look at this first one here. So a lot of it is about reading the problem, knowing what we need to do, and maybe combining a couple of things. So let's look at this problem. This one's got a couple of different things going on. We'll actually need to use a couple of different concepts as we're doing it. Okay. So this one's asking us to calculate probability that a selection of 5 people will actually have 3 men and 2 women in it. All right. So let's ask a different question to start with, because this is actually important. When we, pardon me, want to calculate a probability, we want to know the total number of ways that something can happen, right? So in this particular one, if I'm ignoring the men and women part, I want to calculate the total number of ways first to choose 5 people from a group of 10. That would be the size of your sample space, right? The way they're divided up doesn't matter. If I want to choose 5 people from a group of 10, I need to calculate that first for the size of your sample space, right? Okay. Now, if I'm going to select 5 people from a group of 10, am I going to select the same person 5 times? No. So our repeat's going to be allowed here. No. Okay. So this is going to be without repetition. That's one way to say it. You might also see something to say without replacement. If you say without replacement, that means that once something is selected, it cannot be selected again. That's without replacement. So to give if anybody plays cards, if you see selecting a card hand, for example, that's typically without replacement because you're not going to get 17 aces dealt to you, for example. If you did, somebody's going to shoot you over again. Okay? All right. Pardon me. Anyway, so this is going to be, if you see the words without replacement, that means without repetition, so you're thinking permutation or combination. Okay, that's what without replacement would be. All right, so if I want the size of my sample space, we're going to do without replacement, so permutation or combination. Does the order matter? If I'm just selecting 5 people from a group of 10, do I care about the order? No. So this will be, there's 10 total, and we're going to choose 5. It's a combination. Yes?
Well, you say the size of the sample space is 10.
No, I said the size of the sample space is that. The sample space is how many ways can you select 5 people from a group of 10. So that will be the size of your sample space. Whatever that number turns out to be. It's 10 factorial over 5 factorial times 5 factorial. I can do it with a calculator. Like I said, if you're going to do these and actually do the numbers, you'll want to find out where the button on your calculator is. Okay. I don't expect you to spend all day trying to multiply these things out. Okay. You can do it pretty quickly, actually. If you... Oops. You start with the top number and write as many numbers as there are as you're selecting. So it'd be 10 times 9 times 8 times 7 times 6. Divide by 5 factorial. The 5 and the 2 will go into the 10. The 3 goes into the 6 twice. The 4 goes into the 8 twice. 63 times 4 is what, 252? So it didn't need a calculator. If the numbers get bigger, you'll definitely want a calculator. Okay. But like I said, you can do it by hand quickly. I did this in high school, and we didn't have calculators. This is what you had to do. We did stone tablets back when I was in high school. We do tease Dr. Roth about using stone tablets, though. All right. Is that okay? All right. That part's not bad. Calculating the sample space, not too bad because I need to do the total number of possibilities, right? I'm not worried about categories of things. I need to select 5 things from a group of 10. That's what it would be. The harder part is figuring out what the numerator has to be. I need to select 3 men from a group of 7, and I need to select 2 women from a group of 3. Right? That's 2 different tasks to do, right? I gotta select the men and select the women. If I have 2 tasks to do to figure out the total number of ways, what do I do with those 2 numbers? Multiply them, right? So I'm gonna pick the men, then pick the women, or vice versa, it doesn't matter, as long as you do the 2 tasks, okay? Pick the men, then pick the women, and I'll multiply to get my size of the event. So if my event is, if A is selecting 3 men and 2 women, then what's the size of my event? Good. 7 choose 3 times 3 choose 2. Exactly. 7 choose 3 is the number of way to choose the men. 3 choose 2 is the number of ways to choose the women. We're doing men, then women. Multiply. You could also think of it as women, then men, and multiply. You got the same number. You don't need to worry about doing it in both orders. You just need to do one order. 7 choose 3 is, what is it? 35 times 3, so you get 105. Yeah, I was forgetting my 5. The 6 was canceling, but I was like, what do I need to multiply by the 7? All right, so 105. Now I figured out the total number, so our probability of A will be what? I've calculated both numbers now. What do I do to figure out the probability? Yeah, just divide. Good. 105 over the 252. Good. Exactly right. Okay. 2 things about the answers here. 1, I never, ever care if you reduce a fraction. Especially these problems. Especially when the numbers get big. The calculators will reduce fractions for you, so don't ever bother reducing the fractions. You could not care any less. Okay? And if you wanted to set this problem up all at once and just do it all at once, if you wanted a probability of A here, I would expect that as you get more comfortable with the problems, you would just write it like this. And that tells me you know how to do the problem. You don't have to write all out all the gory details. Okay? And in fact, if you don't even want to type that into your calculator and leave it like that, fine. I don't care. At this point, this is a calculator active type of thing, right? This tells me you understand how to do the problem. I don't care if you simplify it. Okay? I'm going to trust that you will know how to find the button on your calculator and type it in. Yes?
So on test, you don't care for us to find the answer.
Correct. Yeah. Could not care any less. You can get to this point and you're done. That is the answer. That's a number. That's a number. The reason why I'm saying it this way is because the rest of it's calculator. And at that point, you might mistype something in your calculator. At this point, this is the answer. And the rest of it's just spending the time and putting it in your calculator. I don't care. I do not care. Anytime it gets to a point where you can finish off the problem by doing arithmetic, you can stop. Because the rest of it's just arithmetic and you can do it on your calculator. Now, I know there's other things that you can do with your calculator that I am going to want to see. For example, later on, when we do continuous probabilities, you're going to need to integrate. Yes, I know your calculator can do an integral. No, I'm going to want to see the integral. Now, once you plug in the endpoints for your definite integral, I don't care if you simplify it from that point. Does that make sense? It's like literally, if it's an arithmetic computation, I could not care any less to see it. Okay. Now, if you want to go ahead and do it, be my guest. I'm just saying you don't have to. Okay. I go under the assumption that at some point in your life you've been tested over arithmetic. Okay? I don't need to retest you on your arithmetic. All right. We'll do more of these next on Tuesday. We'll probably also get into section 1.3 on conditional probability. So you've got those problems to work on for Tuesday. The other thing I would like you to do for Tuesday is I've got the video posted on Moodle over conditional probability. Go ahead and please watch that before class on Wednesday. Or Tuesday. Whatever day it is. From Tuesday. So anyway, have a good one, everybody. I'll see you on Tuesday, if not before. Some of you I will see tomorrow in Linear.